Welcome to the Explainer. Today we're diving into the absolute, most versatile protagonist of our daily lives. I'm talking about carbon. Seriously, take a second and just look around you right now, or think about your morning routine. You're going to find carbon literally everywhere. It's in the food you just ate, it's woven right into the clothes you're wearing, it's the graphite in your pencil, and, well, most importantly, it's the fundamental building block of all living structures. That includes you and me. Carbon's amazing ability to combine with other elements is exactly what makes life, as we know it, totally possible. But get this, here's a wildly fascinating contrast. Despite forming the basis of all life on Earth and being present in millions of known compounds, carbon makes up a shockingly meager 0.02% of the Earth's crust in the form of minerals like coal and petroleum. And even up in our atmosphere, carbon dioxide accounts for just 0.03%. To put that into perspective, it's practically a rounding error in the grand makeup of our planet. Okay, let's dive into this. How exactly does an element that is so incredibly scarce manage to achieve such monumental importance all across the globe? Seriously, how does so little do so much? Well, to answer that, we really have to look at the unique rules of chemistry that govern this specific, incredible atom. Here's our roadmap for today's explainer. We're going to cover the versatility of carbon, covalent bonds and allotropes, chains, rings, and families, chemical properties and reactions, ethanol and ethanoic acid, and finally, the chemistry of cleaning. All right, Section 1, the versatility of carbon. This is a truly unique element that chemist Friedrich Fuller proved way back in 1828 isn't governed by some mysterious magic, but by pure, undeniable chemistry.
So what actually makes carbon's chemistry so special? Well, it really boils down to three main factors. First step is catenation. Carbon is incredibly friendly. It just loves to, hold hands with other carbon atoms, and it forms these massive long chains, branches, and even loops or rings. Honestly, no other element does this quite like carbon. Second is tetravalency. Since carbon has 4 valence electrons, it can hold hands with up to 4 other atoms all at the same time, whether that's more carbon or oxygen, hydrogen, or nitrogen. And finally, carbon has a very small atomic size. Because it's so small, its nucleus can hold onto these shared electrons incredibly tightly, which creates exceptionally strong and stable bonds.
Moving right along to Section 2, covalent bonds and allotropes. Now, what's really interesting about this is how carbon handles its electrons. Carbon's atomic number is 6, meaning it has 4 outer electrons. Gaining or losing 4 entire electrons is just way too unstable for it, so it solves this problem by sharing them instead. Notice the stark contrast here between ionic and covalent bonds. Ionic compounds, where electrons are completely gained or lost, or actually, scratch that, it's more like they're totally stolen or given away. They have high melting points and conduct electricity super well. But carbon forms covalent bonds just by sharing. Because no charged ions are formed, the intermolecular forces are relatively weak. That's exactly why carbon compounds usually have much lower melting and boiling points, and why they're generally pretty terrible conductors of electricity. But wait, carbon still has a few major tricks up its sleeve, depending on how those atoms arrange themselves. We call these different forms allotropes. If every single carbon atom bonds to 4 others in a super rigid 3D structure, boom, you get diamond, the hardest substance known to us. But if those exact same carbon atoms bond to just 3 others in flat hexagonal layers, you get graphite, which is smooth, slippery, and surprisingly conducts electricity. There's even this wild form called C60 Buckminster fullerene, where 60 carbon atoms arrange themselves perfectly into the shape of a football. It's literally the exact same atoms, just yielding entirely different properties based purely on how they bond together. Okay, Section 3, chains, rings, and families. Let's see how these build up. When carbon bonds primarily with hydrogen, we get hydrocarbons. Building these molecules is a really logical step-by-step process, kind of like snapping together tiny molecular Lego blocks. First, you link the carbon atoms together to form your core skeleton. If you use only single bonds, like in ethane, you've built what we call a saturated compound. Then, step 2, you just plug in hydrogen atoms around the outside until every single carbon has 4 bonds. But sometimes carbons share 2 or even 3 pairs of electrons, forming double or triple bonds. We call these unsaturated compounds, like ethene or ethine. And let me tell you, they are significantly more reactive than their saturated counterparts. And carbon doesn't just stick to hydrogen. Oh no! This dense chemistry jargon you might see actually describes an incredibly simple concept. If you replace just one hydrogen atom on a carbon chain with a different atom, what chemists call a heteroatom, like oxygen or chlorine, it completely changes the compound's entire identity. These swap-ins are called functional groups. For instance, adding an OH group turns a basic hydrocarbon right into an alcohol. And it doesn't matter if the carbon chain is 2 carbons long or 10 carbons long. That one little alcohol group dictates exactly how the chemical behaves, creating what we call a homologous series. That brings us to Section 4, Chemical Properties and Reactions. Let's see these in action. Most of the fuels we use every single day, like the methane gas in your kitchen stove or the petrol powering your car, are carbon compounds. When they burn in the presence of oxygen, they release carbon dioxide, water, and a massive amount of heat and light. If you're burning a saturated hydrocarbon with plenty of oxygen, you get a really clean blue flame. But if you burn an unsaturated hydrocarbon, or if there just isn't quite enough oxygen in the mix, you get incomplete combustion. That results in a yellow, really sooty flame. And that soot? Yeah, that's quite literally just unburnt carbon.
Beyond just setting things on fire, carbon compounds undergo a few other absolutely crucial reactions. Through oxidation, we can use agents like potassium permanganate to forcefully add oxygen to a compound, literally turning alcohols straight into acids. Then there's addition. If you have an unsaturated chain with a double bond, you can use a nickel catalyst to snap that double bond open and add hydrogen. This is exactly the trick the food industry uses to turn liquid vegetable oils into solid, saturated fats. Finally, in a substitution reaction, you can systematically swap out hydrogen atoms for something else, like chlorine, simply by exposing the mixture to direct sunlight.
Section 5, Ethanol and Ethanoic acid, 2 compounds you absolutely know.
So, the crucial point here is that despite both being incredibly simple carbon chains, these 2 compounds are wildly different. Ethanol is an alcohol. It's a fantastic solvent used in medicines like cough syrups. It's the active ingredient in alcoholic drinks, and it's even used as a clean fuel additive. Ethanoic acid, on the flip side, is a carboxylic acid. You probably know a diluted version of it from your kitchen, vinegar. Pure ethanoic acid is often called glacial acetic acid. And the reason for that is it actually freezes into solid ice-like crystals in cold climates.
But here is where the chemistry gets really fun. What happens if you take that ethanol and ethanoic acid and mix them together with just a few drops of an acid catalyst? Well, you get a chemical reaction called esterification. The 2 molecules link up together, they drop a water molecule in the process, and they form what's called an ester. Esters are these incredibly sweet, fruity-smelling substances. Whenever you use synthetic perfumes or taste artificial fruit flavoring in candy, you are experiencing the direct, real-world result of this exact carbon reaction.
And finally, Section 6, the chemistry of cleaning.
Now, if we take that sweet-smelling ester we literally just made and treat it with an alkali, we get soap. That process is known as saponification. But to truly understand how soap actually works to clean things, we have to meet an ingenious, microscopic hero called the micelle. You see, most dirt on our bodies or our clothes is oily, and since water and oil naturally repel each other, plain old water just washes right over the dirt without doing anything. But when you add soap to the mix, the molecules arrange themselves into spherical clusters. These are the micelles, and they act as a perfect, microscopic bridge between the oily dirt and the washing water. And this brilliantly illustrates how a soap molecule pulls this off. It has 2 very different ends. It has a hydrophilic, or water-loving head that faces outward, and a hydrophobic, or water-fearing tail made of a long carbon chain that faces inward. So that long carbon tail burrows deep into the greasy dirt, while the ionic head stays happily out in the surrounding water. When you agitate the water by scrubbing or running the washing machine, these little molecules lift the dirt right off the surface, forming an emulsion that simply rinses away down the drain. But have you ever tried to wash your hands only to find that your soap barely lathers at all, and instead it just leaves behind this weird white, curdy solid in the sink? Yeah, that's what we call the hard water problem. Hard water contains calcium and magnesium ions. When they meet normal soap, they react chemically to form an insoluble precipitate known as scum. It's super annoying. To fix this, chemists developed modern detergents. They're very similar to soap, but they have differently charged ends that specifically do not react with that calcium and magnesium. This ensures your clothes get nice and clean, even if you live somewhere with hard water. So we've traveled all the way from the microscopic sharing of a single valence electron, through complex chains, rings, and burning flames, right to the literal reason you can wash oily dirt off your hands. Carbon's incredible, unmatched versatility literally builds the physical world around us. So the very next time you write with a pencil, eat a delicious meal, or even just wash your clothes, ask yourself, what other invisible chemical heroes are quietly shaping your everyday world? Thanks so much for joining me on The Explainer today, and keep exploring.